Good day, this is the Professor, CBMZ PhD, and today's Monday, May 11th, 2026. It is 10:41 and 12 seconds, p.m. Eastern Standard Time, and today's research, lasers and a scientific dream. So let's hop to it here. Following the major development, there was much speculation about the possibility of extending the principle to the optical region. Indeed, the first lasers, light amplification by stimulated emission of radiation, were called optical lasers. The difficulty, of course, was that optical wavelengths are so tiny, about 1 in 10,000 of the microwaves. The major principle depended upon a physical resonator, a box of a few centimeters, or even millimeters, in length. By 10 millimeter wavelength, such resonators are already so small that they are hard to make accurately. Making a box 1 to 1,000 that size was out of the question. Another approach was necessary. In 1958, Bell Telephone Laboratories outlined a theory proposed a structure for an optical laser. They suggested that resonance could be obtained by making the waves travel back and forth along a relatively long, thin column of amplifying substance that had parallel reflectors at the ends. Ruby is an aluminium oxide in which a small fraction of the aluminium atoms in the molecule structure, or lattice, have been replaced with chromium atoms. These atoms absorb green and blue light, and hence impart a red color to the ruby. The chromium atoms can be boosted from the ground state into excited states when they absorb the green or blue light. This process, by which population inversion is achieved, has been given the name pumping. Pumping in a crystal laser is generally achieved by placing the ruby rod within a spiral flash lamp that operates like those used in high-speed stroboscopic photography. When a lamp is flashed, a bright beam of red emerges from the ruby, shining out through one end, which has been only partially silvered. The duration of this flash of red light is quite brief, lasting only some 300 millionths of a second, but it is very intense. In the early lasers, such a flash reached a peak power of some 10,000 watts. When the device was successfully built and operating, a public relations expert was called in to help introduce this revolutionary device to the world. Lasing begins when an excited atom spontaneously emits a photon parallel to the axis of the crystal. Photons emitted in other directions merely pass out of the crystal. The photon stimulates another atom in its path to contribute a second photon in step and in the same direction. The process continues as the photons are reflected back and forth between the ends of the crystal. We might think of lone soldiers falling into step with a column of marching men. The beam builds up until, when amplification is great enough, it flashes out through the partially silvered mirror at the right, a narrow, parallel, concentrated, coherent beam of light. Application of lasers can be divided into two broad categories. One, commercial, industrial, military, medical uses, and two, scientific research. In the first case, lasers are used to do something that has been done in another way up to now, but not as well. Sometimes a laser solves a particular problem. For example, one of the first applications was in eye surgery for welding a detached retina. The laser is particularly useful here because laser light can penetrate transparent objects, such as the eye's lens, eliminating the need to make a cut into the eye. Surgeons have long wanted a better technique for treating extremely small areas of tissue. A laser beam, focused into a small spot, performs perfectly as a Lilliputian surgical knife. An additional advantage is that the beam, being of such high intensity, can also sterilize or cauterize tissue as it cuts. The narrowness of the laser beam has made it ideal for applications requiring accurate alignment. Perhaps the ultimate here is the 2-mile-long linear accelerator built. Aerostraight would not have been nearly good enough to assure expected performance. The narrowness of the laser beam has made it ideal for applications requiring accurate alignment. Perhaps the ultimate here is the 2-mile-long linear accelerator built. arrows straight would not have been nearly good enough to assure expected performance. A laser beam was the only technique that could accomplish the incredible task of keeping the 7/8 inch bore of the accelerator straight along its 2-mile length. A remote monitoring system based on the same laser beam tells operators when a section of the accelerator has shifted out of line, due for the example to small Earth movements by more than about 1 to 32 inch, and identifies the section. The large tube houses the optical alignment system and supports the smaller accelerator tube above. Target patterns dropped into the large tube at selected points produce an interference pattern at the far end of the tube similar to the one in the precise alignment of the tube is achieved by aiming the laser at the center dot to the pattern. Then the section that is out of line is physically moved until the dot appears in the proper place at the other end of the tube. It is the extreme coherence of the laser beam that makes this technique possible. Having heard that laser light bored through steel and is being used in micro-welding, some have asked whether the laser will ever be used to weld bridge members and other structural girders. This is missing the whole point of the laser. It would be like washing your floor with a toothbrush, even one with extra stiff bristles. There would be no advantage to using lasers for large-scale welding. Present equipment for this operation is quite satisfactory and far less wasteful of input power. The sensible approach is to use lasers where existing processes leave something to be desired. Until the advent of the laser, for example, there was no good way to weld wires 0.001 inch in diameter, nor was there a good way to bore a tiny hole in the diamond that is used as a die for drawing such fine wire. It used to take 2 days to drill a single diamond. With laser light the operation takes 2 minutes, and there is no problem with rapid wear of a cutting tool. So much for the first category of application. In the second category, namely use of the laser as a scientific tool, we enter a more theoretical domain. Here we use coherent light as an extension of ourselves to probe into and to look at the world around us. Much experimental science is a matter of cooling, heating, grinding, squeezing, or otherwise abusing matter to see how it will react. With each new tool, ultra-fast centrifuges, high and low pressure, and extreme temperature chambers, intense magnetic fields, atomic accelerators, and so on, more has been learned about this still puzzling world. Since coherent light is something new, we can do things to matter that have not been done before, and see how it reacts. The laser is being used to investigate many problem areas in biology, chemistry, and physics. For example, sound waves of extremely high frequency can be generated in matter by subjecting it to laser light. These intense vibrations may have profound effects on materials. In the chemical field, the sharp beam and monochromatic energy of the laser hold great promise in the exploration of molecular structure and the nature of chemical reactions. Chemical reactions usually are set off by heat, agitation, electricity, or other broadly applied means. None of these energizers allow the fine control that the laser beam does. Its extremely fine beam can be focused to a tiny spot, thus allowing chemical activity to be pinpointed. But there is a second advantage. The monochromaticity of coherent light also makes it possible to control the energy, in addition to the intensity of the beam, accurately by simply varying the wavelength. Thus it may be possible, for instance, to cause a reaction in one group of molecules, but not another. One application in chemistry that holds great promise is the use of laser energy for causing specific chemical reactions, such as those involved in the making of plastics. Bell Telephone laboratory scientists have changed the styrene monomer, a raw plastic material, to its final state. Polystyrene in this way The success of these and similar experiments elsewhere opens for exploration, a vast area of molecular phenomena. In another scientific application, the laser is being used more and more as a teaching tool. Coherence is a concept that formerly had to be demonstrated by diagrams, formulas, and interference from experiments. The laser makes it possible to see coherence in action, along with many of the physical effects that result from it. Such phenomena as diffraction interference, the so-called iridescent patterns, and spatial harmonics, always difficult to demonstrate to students in the abstract, can now be seen quite concretely. Other interesting things can also be seen more plainly now. Laser light is being used to look at plasmas. Plasmas are ionized gaseous mixtures. Their study lies at the heart of constant search by atomic scientists for a self-sustained controlled fusion reaction that can be used to provide useful nuclear power. This kind of reaction provides the almost unlimited energy in the sun and other stars. It is more efficient and releases less radioactivity than the other principal nuclear process, fission, which is used in atomic electric power plants. On the other hand, have used the concentrated energy of the laser, not to look at, but to produce a plasma. They blasted an aluminium target the size of a pinhead with a laser beam, thereby vaporizing it and creating a plasma. The calculated temperature in the electrically charged gas was 3 million centigrade. This is pretty hot, but still not hot enough for a thermonuclear reaction. The temperature of a plasma necessary to sustain a thermonuclear reaction is so high above 10 million degrees Celsius that any material is vaporized instantly on coming into contact with it. The only means developed so far to contain the plasma is an intense magnetic field, or magnetic bottle. Containment has been accomplished for only a few thousandths of a second at most. It is almost self-evident that no single device, even one as incredible as a laser, could accomplish all the feats mentioned in the preceding paragraphs. After all, some of these applications require high power, but not extremely high monochromaticity, while in others, the reverse may be true. Yet, by its very nature, any laser produces a beam with one, or at least most a few, wavelengths, and many different materials would be needed to provide the many different wavelengths required for all the tasks listed. Also, the first laser was a pulse device. Light energy was pumped in, and a flash of energy emerged from it. Then the whole process had to be repeated. Pulse operations is fine for spot welding, and for applications such as radar type, range finding, where pulse of energy are normally used anyway. With lasers, small objects can be detected than when using the usual microwaves, but a pulse process is not useful for communications. In other words, pulsing is good for certain applications, but not for others. And of course, solid crystals are difficult to manufacture. Hence, it was natural for laser pioneers to look hopefully at gases. Gas lasers would be easier to make. Simply fill a glass tube with the proper gas and seal it. Other advantages would accrue. For one thing, the relatively sparse population of emitting atoms, and the gas provides an almost ideally homogeneous medium. That is, the emitting atoms corresponding to chromium in the ruby crystal are not contaminated by the lattice or host atoms. Since only active atoms need to be used, the frequency coherence of a gas laser would probably be even better than that of the crystal laser. Their reasons. Gas lasers now utilize many different gases for different wavelength outputs, and powers and provide the purest light of all. An additional advantage is that the optical pumping light could be dispensed with. An input of radio waves of the proper frequency did the job very nicely. But most significant of all, Javon's gas laser provided the first continuous output. This is commonly referred to as continuous wave operation. The distinction between pulse continuous wave operation is like the difference between baking one loaf of bread at a time and putting the ingredients in one end of a baking machine and having a continuous loaf emerge at the other. When a non-expert thinks of a laser, he is apt to think of power-blinding flashes of energy. As we know, this is only a small part of the capability of the laser. Nevertheless, since lasers are often specified in terms of power output, it may be well to discuss this aspect. The two units generally used are joules and watts. You are familiar with a watt and have an idea of its magnitude. Think, for example, of a watt, or a 150-watt bulb. A watt is a unit of power. It is the rate at which electrical work is being done. The joule is a unit of energy and can be thought of as the total capacity to do work. 1 joule is equivalent to 1 watt-second, or 1 watt applied to 1 second. But it also can mean a 10-watt burst of laser light lasting 0.1 second, or a billion watts lasting a billionth of a second. In general, the crystal ruby lasers are the most powerful, although other recently introduced materials, such as liquids, and specially prepared glass are providing competition. With proper auxiliary equipment, bursts of several billion watts have been achieved, but the burst lasts only about 100 millionths of a second. For certain uses, that is just what is wanted, a highly concentrated burst of energy that does its work without giving the material being down a chance to heat up and spread the energy, perhaps damaging adjacent areas. Since the joule gives a measure of the total energy in a laser burst, it is not applicable to continuous wave output. Power in this area began low, in the milliwatt 1/1000th of a watt region, but has been creeping up steadily. A recent gas laser, utilizing carbon dioxide, has already reached 550 watts of continuous infrared radiation. An advantage of gas and liquid lasers is that they can be made just about as large as one wishes. One of the least satisfactory aspects of the laser has been its notoriously low efficiency. For a while, the best that could be accomplished was about 1%. That is, 100 watts of light had to be put in to get 1 watt of coherent light out. In gas lasers, the efficiency was even lower, ranging from 0.01% to 0.1%. Lasers, this was no great problem, since high power was not the objective. But with the high-power solid lasers, pumping power could be a major undertaking. A high-power laser pump built by Westinghouse Research Laboratories handles 70,000 joules. In more familiar terms, the peak power input while the pump is on is about 100 million watts. For a brief instant, this is roughly equal to all the electrical power needs of a city of 100,000 people. Two relatively new developments have changed the efficiency levels. 1. The carbon dioxide gas laser is quite efficient, with the figure having passed 15%. The second is the injection or semiconductor laser, in which efficiencies of more than 40% have been obtained. Unless unforeseen difficulties arise, this figure is expected to continue to rise to a theoretical maximum of close to 100%. The semiconductor laser is too solid, and gas laser is what the transistor was to the vacuum tube. All the functions of the laser have been packed into a tiny semiconductor crystal. In this case, electrons and holes, vacancies in the crystal structure that act like positive charges, accomplish the job done by excited atoms in the other types. That is, when they are stimulated, they fall from upper energy states to lower ones, and emit coherent radiation in the process. Aside from this, the principle of operation is the same. The device itself, however, is vastly different. For one thing, it is about the size of this letter O. For another, it is self-contained, since it can convert electrical current directly into laser light. The first time this has been possible, an external pumping source is not required. This makes it possible to modulate the beam by simply modulating the current. A different approach has been to modulate a magnetic field around the device. This, it turns out, can also be done with some newer solid crystal lasers. An additional advantage offered by the semiconductor laser is simplicity. There are no gases nor liquids to deal with, no glassware to break, and no mirrors to align. Although it will not deliver high power, it can already deliver enough continuous wave power for certain communications purposes. Its simplicity, efficiency, and lightweight make it ideal for use in space. Future deep space missions are expected to require extremely high data transmission rates, on the order of 1 million bits per second, to relay the huge quantities of scientific and engineering information gathered by the spacecraft. Higher data rates are necessary to increase both the total capacity and the speed of transmission. By comparison, the Mariner 4 spacecraft that sent back TV pictures of Mars had a data rate of only 8 bits per second, 100,000 times too small for future missions. The use of lasers would mean that the results could be transmitted to Earth in seconds instead of the 8 hours it took for the photos to be sent from Mariner 4. One of the problems to be solved in using lasers for deep space communication, oddly enough, is that of pointing accuracy. Since the beam of a laser energy is narrow, it would be possible for the radiation to miss the Earth altogether and be lost entirely unless the laser were pointed at the receiver with extreme precision. Aiming a gun at the target 50 yards away is one thing. Aiming a laser from an unmanned spacecraft 100 million miles away is quite another. It is believed, however, that present techniques can cope with the problem. Another peculiarity of laser communication is that it will probably be accomplished faster and more readily in space than here on Earth. Powerful though laser light may be, it is light and is therefore impeded to some extent by our atmosphere even under good conditions. Data transmissions of 20 and 30 miles have already been accomplished in good weather with lasers. But if you have ever tried to force a searchlight beam or shine automobile headlights through heavy fog, rain, or snow, you will appreciate the magnitude of the problem under these conditions. The use of infrared frequencies helps to some extent, since infrared is somewhat more penetrating, but the poor weather problem is a serious one. Atomic energy, only a scientific dream a few short years ago, is now providing needed power in many parts of the world. In the same way, a laser, also an atomic phenomenon, has made its way out of the laboratory and into the fields of medicine, commerce, and industry. If it hasn't touched your life as yet, you need only to be patient. It will. Indeed, the most exciting probability of all is that lasers undoubtedly will change our lives in ways we cannot even conceive of now. And this video was created for educational purposes only. Hope you enjoyed listening. My code name is Will. I'm Professor Christopher Brunet, leader of research scientist, ufologist, psychic computer technician, computer programmer, philanthropist, writer, mathematician, artist, photographer, film producer, chef, animal, and nature lover. My passion is world peace. Hope you have a great day. Thanks for listening. Good day. This is the Professor, CBMZ PhD. And today